Anushri? Yeah, we can start. We can start.
Yeah, we can start. Okay, hello everyone. So today we would be solving MCQs related to UV visible spectroscopy, and I will be discussing each MCQs, and I will also teach you how to approach each of these MCQs carefully. So we have a set of 20 questions. So in minimum time, we will try to attempt maximum questions at the fastest pace possible. I hope everyone is ready. So let us have a look at our very first MCQ. The question is, the increment for alpha alkyl substitution on enones is, options is 18, option B 12, option C 10, and option D 5. Now we all know about the Woodworth-Fisher rule, where we have different additions for different alkyl groups, like there is an alkyl group substitution. तो उसमें क्या होगा, if there is a halide group substitution, तो उसका increment कितना होगा. So adding that value will get the total lambda max of the compound. So there is a fixed table which, if you will refer for UV spectroscopy, because now we have limited time, I cannot discuss all the increment lambda max values of each functional group. So I will, if you refer the chart for alkyl substitution on enones, every alkyl substitution increment will have which of the following, that is 18, 12, 10 or 5. The answer is 10. So every alkyl substitution on any functional group or any compound having an enone is going to be 10. So let us proceed to the next. So all these information about the alkyl substitutions, like for beta or gamma substitutions, I think the increment is 18. So accordingly, if you'll refer the chart and memorize it, you'll be able to approach this MCQ very soon. Moving on to the next question. If a sample exhibited has an absorbance of 1 in UV visible spectroscopy, the percentage transmittance will be, we have option A 1%, option B 0.1%, option C is 10%, option D is 0.01%. Now we are all aware that absorbance is given by the formula 2 minus log in bracket transmittance T. So when you substitute the value, it is very simple. So percent transmittance becomes antilog of 2 minus the absorbance. So what is our absorbance given in the question? It is 1. So 2 minus 1 gives you 1, and antilog of 1 is 10. So the percent transmittance for any compound having an absorbance of 1 in UV visible spectroscopy is going to be, our answer is 10%. So you have to remember this formula, which is derived from the Beer-Lambert's law. So when you will study about the Beer-Lambert's law, you will get the multiple equations from it. And the simple equation is, to calculate absorbance, the formula is 2 minus log percent transmittance. Now, if you have to find percent transmittance, then while rearranging the formula, we get it as percent transmittance equals to antilog of 2 minus absorbance. So absorbance in the question is 1. So 2 minus 1 is 1, and antilog of 1 is 10. So the percent transmittance, our answer is 10%. Moving on to the next question. Absorbance of materials used for making collimating systems in comparison to instrument wavelength should be which of the following? We have option A, less than 0.2%, option B, more than 0.2%, option C, less than 0.1%, and option D is more than 0.1%. So as you can see, absorbance of any material. Now, what is the function of a collimating lens? The collimating lens is basically going to rearrange all the UV light that is going to enter your sample. So it will allow light of specific wavelength to hit onto your sample. So it is very important that a proper wavelength absorbance is maintained of the material, because what happens, the construction of material of the collimating lens should not interfere with the UV absorbance of the sample when it is being calculated by the UV spectrophotometer. So also it should not be very less also. So the optimum required is less than 0.2%. So the correct option is the absorbance of materials which will be used for making a collimating system in comparison to the instrument wavelength should be less than 0.2% so that it does not interfere or create background noise when compared with the instrument wavelength. So our answer is less than 0.2%. So let us save and move on to the next. Now, what are the dimensions of molar absorptivity in Beer's law expression? So now, if you remember the Beer-Lambert's law, we have the following options: mole per liter, liter per mole into centimeter, then option C is grams per mole, and option D is microgram per centimeter square. Now, as you know, the Beer-Lambert's law, according to the derivation of the Beer-Lambert's law, let us eliminate one option one by one. Now, option C, grams per mole, is basically going to be the dimensions for the mass of a product. So it is the dimension related to the mass spectroscopy. So any molecular weight, when you're going to estimate by using the mass spectroscopy, is given by the terminology of grams per mole. It cannot be microgram per centimeter square because we don't have any surface area related equation or element in our Beer-Lambert's law. So I will eliminate the option C and D. Now I have options A and I have options B. Now it is moles per liter, or it can be liters per mole into centimeter. Now since it is not centimeter square, but centimeter may be there in the Beer-Lambert's law. Why? Because it also depends upon the path length. So basically the length of the cuvette in which you're going to place your sample. So that also becomes a deciding factor for your UV absorbance. So length, that is basically the path length, is also important. So it is not moles per liter because Beer's law will not cannot eliminate the path length. So option A is also eliminated. So our only possible option, which is the answer, is the option B, which is liter per mole into centimeter. So let us move on to the next question. All of the following are useful as a source of UV visible, except which of the following are not a source of UV visible. That is what the question means. So we have option A, glow bar source. Second option, xenon discharge lamp. Option C, deuterium discharge lamp. And the last option is tungsten filament lamp. Now, if you look at all the options carefully, so let us go by one by one in all the options. We have the glow bar source, then we have xenon discharge lamp, then we have the deuterium discharge lamp and the tungsten filament lamp. So what does the question say again? All of the following are useful as a source of UV, except which of the following? So the answer is very simple. It is the glow bar source. Why? Because glow bar source is a source for IR spectroscopy. So you don't have to waste time on the remaining three options because the first option that you have approached itself is incorrect, because we all know that the glow bar source is extensively used for IR. So our option is going to be the glow bar source. Rest of the sources, xenon discharge lamp, deuterium discharge lamp, and tungsten filament lamp are all useful for the UV visible spectroscopy. So the only one which is not a source of UV visible is our glow bar source. So let us select this option and proceed. So as you can see, in 1 minute and 30 seconds, we have solved 5 MCQs. So let us rapidly move on to the next. In UV visible spectroscopy, Beer's law is related to concentration and Lambert's law is related to path length of the absorbing species. Is it true or is it false? So now in all of these questions, I have always been asking you that, are you aware of the Beer-Lambert's law? Are you aware of the Beer-Lambert's law? And I also mentioned that the Beer-Lambert's law has all the equations in it. It is related to the concentration. It is also related to the path length. So basically, so the answer is true. So in UV visible spectroscopy, Beer's law is related to concentration, as we all know, and the Lambert's law is related to the path length of the absorbing species. So let us choose the answer true and move on to our next MCQs. And we all know about the Beer-Lambert's law equations also. It is A equals to epsilon BC, where A is the absorbance, epsilon is denoted as the molar absorptivity, B is the path length, and C is the concentration. So Beer's law and Lambert's law combined makes the Beer-Lambert's law, and the equation for the combined Beer-Lambert's law is absorbance equals to the molar absorptivity multiplied by the path length and multiplied by the concentration. So the path length is nothing but the length of the light path. Next question, which of the following shows bathochromic shift in a polar solvent? Now, do you know what is bathochromic shift? You must have known that bathochromic shift is basically shift towards higher wavelength. So there are many multiple factors that affect your bathochromic shift. So there are bathochromic shift, there is also hypsochromic shift, there is there are various shifts. So bathochromic shift is basically a shift of a peak or signal towards the longer wavelength. So there are many solvents which promote the compound to undergo a bathochromic shift. So there are multiple factors that may either cause the compound to go bathochromic shift or may lead to a hypsochromic shift, which is shift towards the lower wavelengths, that is the shorter wavelengths. So which can be the factors? We have option A, water, we have option B, ethanol, we have option C, ethylene, and we have option D, chloroform. So this is a little tricky. So how will I know that these is going, one of these options have to be eliminated? Now it cannot be water. Why it cannot be water? Because water is very polar in nature. So it will not contribute to a very high extent to aid the bathochromic shift of a compound. So basically, bathochromic shift will occur because of the formation of hydrogen bonds between the compound and the solvent molecules. So water has only 2 hydrogen bonds and will not be actively involved in hydrogen bonding. Same goes for ethanol. Ethanol will also not be actively involved. And option D, chloroform, which is not polar at all. The polarity of chloroform is very much lesser compared to water and ethanol, and chloroform is an organic solvent and is comparatively non-polar. So the only remaining option is ethylene. So ethylene comparatively will form stronger hydrogen bonds with the polar solvent. So that is the reason why, because of the strong hydrogen bonding, the shift towards a longer wavelength or a bathochromic shift is going to occur. So our answer here is ethylene. So let us save and move on to our next question, which is dimerization of a sample produces which of the following? That is option A, absence of absorbance, option B, hypsochromic shift, option C, bathochromic shift, and option D, no effect at all. So now dimerization, what does dimerization mean? Dimerization is basically 2 monomers reacting with each other to form a dimer. So when 2 monomers are reacting with each other and bonding to form a dimer. So dimerization will not result to the absence of absorbance. Why? Because since 2 monomers are added up, the UV absorbance will be accounted for both the monomers as an entire entity. So there will be absorbance. Next, hypsochromic shift, it cannot occur at a lower wavelength. Why? Because dimerization is forming a strong bond between 2 monomers. So both these monomers collectively will have a higher wavelength than have a lower wavelength compared to each of the monomer. मतलब क्या? Individual monomer का जितना भी lambda max या absorbance है, उसका double होगा. Because why? Because both the monomers are forming and binding into form a dimer. So hypsochromic shift भी नहीं होगा. Hypsochromic shift means shift towards shorter wavelength. तो shorter wavelength में absorbance shift होना is not possible in this case. And option C is bathochromic shift, and option D is no effect. See, option A and option D almost mean the same, because if there is an absence of absorbance, there is going to be no effect. And no effect means your peak in the UV spectrophotometer is not going to be detected because there has been no absorbance occurring. So option D also gets automatically eliminated. So the only possible answer which remains is the option C, which is bathochromic shift. So our answer here is bathochromic shift. Moving on to the next. How should the concentration of colorless samples be determined? Using UV spectrophotometer. Option B, using visible spectrophotometer. Option C is using either UV or visible spectrophotometer. And option D is using an indicator solution and pH solution. Now, let us eliminate the options one by one. Option A is using UV spectrophotometer. This likely seems to be my answer. Why? Because the exact purpose of UV spectrophotometer is to determine samples in both the UV as well as the visible range. But now, since the option is exclusively related to the UV spectrophotometer, so basically you have hyphenated instrument where your instrument can detect compounds which are absorbing at both the visible region as well as the UV region. So when you are having an instrument which is capable of detecting both in the UV as well as the visible region, then you will call it as a hyphenated UV visible spectrophotometer. Sometimes only if your instrument is capable of operating in the UV range only, then that instrument will be exclusively called as a UV spectrophotometer only. So I am saying that my option is A. Now, why is B not the option? Why? Because if it is colorless, it is very less likely to be detected in the visible spectrophotometer. Because mostly it is the colored compounds which have a little pigment or tinge which are going to be detected in the visible spectrometer. Why? Because colored solutions absorb at the visible range. So it cannot be either UV or visible spectrophotometer either. Why? Because if you're using a hyphenated technique, so it is, if you're not going to use the proper wavelength range or if you're not going to set the proper scan length, तो ऐसा हो सकता है कि there might be inaccurate analysis where if you're operating only at a visible range, then the compound will go undetected. And if you're operating only at a UV range, then only it may be detected. So the possibility of an analyst error is very high in a UV visible or. And also the option means कि UV में भी detect हो सकता है और विजिबल स्पेक्ट्रोफोटोमीटर में डिटेक्ट हो सकता है. यूवी में डिटेक्ट हो सकता है लेकिन विजिबल स्पेक्ट्रोफोटोमीटर में नहीं डिटेक्ट हो सकता. सो दैट इज व्हाई ऑप्शन सी इज आल्सो नॉट योर ऑप्शन. सो ऑप्शन बी, ऑप्शन सी इज एलिमिनेटेड. नाउ using an indicator solution and a pH paper will not give you the concentration. Why? Because it is a qualitative estimation. Because whenever you are doing a titration, so it is just that you have to calculate with the titration endpoint and everything. And the pH paper is highly inaccurate because when you will just keep the pH paper, it will only tell you what is the pH of the solution, because the pH paper will give a different color based on the acidity and basicity of the solution. So it will not help you determine the exact nature of your compound or the concentration, because it is a semi-quantitative technique, and it is a semi-quantitative technique, and it is not entirely a quantitative technique. So that is why an indicator solution and pH paper is not the answer. So our answer is using a UV spectrophotometer. It will give you a proper peak, and because of the Beer-Lambert's law, it will be directly proportional to the concentration of your sample. So the absorbance will give you the concentration of your sample. So basically from the peak of the compound, that is the UV peak that you will get from the spectra that the spectrophotometer will produce, you can find out the concentration of the colorless sample. Moving on to the next, sample window used in UV is made up of which of the following? Is it option A, glass? Is it option B, quartz? Or is it option C, metal halides? Or is it option D, both A and B? Now, metal halides is never a material of construction for UV. Why? Because metal halides are not transparent. They are not UV transparent, and they will interfere with your reading, or they will produce a background noise of its own. So that is the reason why sample window used in UV, I will say, is made up of both either glass or quartz. It is not metal halides. So I will eliminate option C. As I am saying, glass से भी बनता है, quartz से भी बनता है, तो मैं दो option select नहीं कर सकती. So for that we have a solution which is there in MCQ number D, which is both A and B. So my answer is both A and B, because sample window using UV is made up of glass as well as quartz. So this is, we have see in a matter of 20 minutes or 22 minutes, we have answer 10 MCQs. So 50% of our job is done. So moving on to the next question. How much range of wavelength is transmitted by silicate glass? Now every element has their fixed wavelength of transmission. So how much wavelength will silicate glass produce? So depending on if you roughly for GPAT MCQs, when you will be approaching such type of questions, you will have to memorize the different absorbance range, like silicate glass ka kitna hoga, because it is also important, because it is, if you're going to use silicate glass as your material of construction machinery, so you will have to know whether it is interfering with the analysis or no. So roughly there are certain solvents, uska bhi tumhe lambda max ya wavelength ka range roughly memorize karna hai, so that it would be easy for you to answer these questions. So it is not 100 nanometer to 200 nanometer. It is not 200 nanometer to 300 nanometer. Why I am saying this? Because the wavelength of silicate glass is fixed, because the material is the same. It is not going to change. The absorbance, even if you're using any instrument, the wavelength of absorbance will always be fixed for a particular compound, substance, or a particular functional group. तो सिलिकेट ग्लास के लिए फिक्स्ड है वेवलेंथ. तुम कौन से भी इंस्ट्रूमेंट में सिलिकेट ग्लास को एनालाइज करने की कोशिश करो, उसका वेवलेंथ हमेशा रेंज ऑफ वेवलेंथ जो ट्रांसमिट होता है, दैट इज ऑलवेज गोइंग टू बी फिक्स्ड, एंड द वैल्यू फॉर इट व्हिच हैव बीन प्री डिटरमाइंड इज 300 नैनोमीटर टू 350 nanometer. So it is not option D. So this is a very practical question which you will have to keep it in your memory, because this is a memory based question and it is not a logical question. So this is something purely based on how deep you are going to study. These minor things also matter a lot when it comes to MCQs, because you never know from where these MCQs will be adapted. So basically basic knowledge, just simple basic knowledge hota hai, that also if you will apply these, it will be very easy to memorize things and approach such questions. So moving on to the next, which of the following compounds shows peak in the vacuum UV region? Option A, benzene. Option B, butadiene. Option C is methane, or is it option D, naphthalene? So now how do I approach this question? Basically UV light is having a range of 200 to 600 nanometer approximately. So UV light में जो UV range में जो vacuum region होता है, that is 100 to 200 nanometer. So the vacuum region of the UV wavelength is 100 to 200 nanometer. So basically the only substance which is absorbing at the 100 to 200 nanometer range is methane. Why? Because benzene has a higher wavelength and it will not absorb in the vacuum region, but it will absorb in the UV region. Why? क्योंकि उसका lambda max या wavelength इतना absorbance उसका इतना कम नहीं है. So among all these compounds, such as benzene, butadiene, naphthalene, these are all complex compounds. So benzene is a 6-membered ring. So butadiene is also a diene, and naphthalene. So these are all a larger molecule compared to methane. So obviously they will show a larger lambda max value. So the only compound which has the least lambda max value or the least wavelength of absorbance is methane. So because methane has an absorbance of ranging between 106 to 160 nanometer, it is the compound which will show a peak in the vacuum UV region. So analysis is never carried out in the vacuum UV region. So methane is the only compound which is present in which will show a peak in your vacuum UV region. So moving on to the next, all of the following expressions are correct except P equals to transmitted incidence of transmitted light divided by light, that is incident light and transmitted light. So basically transmittance equals to the intensity of transmitted light divided by the intensity of incident light, or is it option B, absorbance equals to minus log T, or is it option C, absorbance equals to 2 minus log percent T, or is it absorbance equals to minus log of intensity of incident light divided by the intensity of transmitted light? So as we know, option A, that is transmittance, is nothing but the intensity of transmitted light divided by the intensity of incident light. So option A is the correct expression. Option B, A equals to minus log T, is also correct based on the Beer-Lambert law. So this expression is also correct. Option C, absorbance equals to 2 minus log percent T, is also correct. And we have also calculated the percent transmittance using this formula, if you remember our very first MCQ. So A equals to 2 minus log percent is also correct. Now the option which is remaining is option D, which is A equals to minus log of incident light, intensity of incident light divided by intensity of transmitted light. Now why is it incorrect? The percent T transmittance kya hai? It is IT divided by I0. So percent transmittance also has to be anti-log of IT divided by 0, but here the equation is reversed. So this is an incorrect expression because यहाँ पे the correct expression should be log of transmitted light divided by incident light, which is not the case here. So the only incorrect expression here is option D. So even if you're not able to find out why option D is incorrect, you will obviously know that option A is correct, option B is correct, option C is correct. So जो incorrect नहीं है, obviously चारों options तो incorrect नहीं होंगे because that will not justify the question. So you can easily use a practical approach to solve this kind of an MCQ by selecting option D. If your concepts about the derivation is very clear, then it will not be a problem at all to solve this problem. In case your concepts are not clear, then you should know that transmission is intensity of transmitted light divided by intensity of incident light. So option A is the right answer. Option B is also the right answer. Option C is right and option D is incorrect. So let us save and proceed to the next. A collimator is a device used in a monochromator to, option A, focus on the required range from other amines, or option B, eliminate interferences from other amines, option C, eliminate reflection and scattering, and option D, focus the incident radiation parallel onto the dispensing device. Now we will approach this question by the elimination principle. So how are we going to eliminate the option? Option A is focus on the required range from other amines. Now, you know all that the UV spectrophotometer is not exclusive for determining amines. So ऐसा नहीं है कि वो सिर्फ required range other amines का focus करेगा. So option A is not your answer. Option B, if it is not focusing, it will neither eliminate any interferences which are coming from other amines because it is not exclusive to the analysis of amines itself. So option B is also not your answer. And option C, it will eliminate reflection and scattering, which is also incorrect. Why? Because it cannot eliminate reflection and scattering, because the sole purpose of a collimator is to focus the incident radiation onto your sample so that the incident light passes through your sample and then the absorbance can be detected. So the sole purpose of the collimator is your option D, which is to focus incident radiation parallel onto a dispensing device through which it will pass through your sample, and that particular wavelength of light will interact with your sample and the sample molecules will interact with the light which has entered and it will give you that particular absorbance. So the option is answer D. Moving on, absorbance, which is also designated as A in Beer-Lambert's law, is sometimes also called as A, molar absorptivity, B, intensity, C, optical density, and D is none of the above. So as you know that absorbance also designated an A is not molar absorptivity. Why? Because molar absorptivity is designated as epsilon in your Beer-Lambert equation. Intensity is designated as I. So absorbance does not mean intensity. Why? Because intensity basically designates the intensity of the incident light which is falling on your sample. So it has no relation with the absorbance, although it governs and is an important factor for calculating your absorbance, but it is not, intensity is not the answer. Now we have option C and D. None of the above can be a possible answer, but I will tell you why none of the above is not an answer, and the answer is option C. Optical density. Why? Because optical density is nothing but the quantity of light absorbed by a solution. So absorbance is nothing but the measure of the quantity of incident light it has absorbed, and that is the reason why it is giving you that absorbance value. So absorbance is also called as optical density. So optical density is a synonym for absorbance. So our answer is option C, optical density. Why? Because the meaning of absorbance and optical density is literally the same, which means the quantity of light absorbed by a solution. So जितना तुम्हारा सैंपल वो लाइट अब्सॉर्ब करेगा, उस absorbance के basis पे तुम्हें वो absorbance का value मिलेगा. So that is how you will identify the concentration of the sample because of how much of light your sample has absorbed. So optical density is your answer. So saving and moving on to the next question. For calibration of resolution in UV, following is used. Option A, we have holmium filter. Option B, we have polystyrene. Option C, we have toluene and hexane. And option D, we have potassium dichromate. Now, let us solve each of these MCQs carefully. Holmium filter is also used for calibration of UV spectroscopy. Polystyrene is not an option used for calibration of UV spectroscopy. Why? Because polystyrene is exclusively used for calibration of FTIR, that is Fourier transform infrared spectrophotometer. So we will easily eliminate option B. Now option C, toluene and hexane, and option D, potassium dichromate. Now calibration में all the three other options, which is holmium filter भी use होता है, toluene and hexane भी use होता है, and potassium dichromate भी use होता है. But what is the individual role of each of these reagents that you will use? So that also you have to read carefully about the calibration. So जब तुम calibration of UV spectrophotometer read करोगे, so you'll have to remember the role of each of the calibrating solutions carefully. Holmium filter use होता है wavelength accuracy measurement करने के लिए, and potassium dichromate is used to measure the to calibrate the absorbance, that is the absorbance capacity of the instrument. So toluene and hexane is the remaining option. So holmium filter is not used for calibration of resolution. Why? Because it is used for the wavelength calibration, that is the wavelength accuracy calibration. Polystyrene is used for FTIR calibration, and option D, potassium dichromate, is used for UV calibration, but not for the parameter resolution. It is used for calibration of the parameter absorbance. So the parameter for which the calibration reagent used for resolution is the toluene and hexane. So अगर तुम्हें resolution parameter UV spectrophotometer calibrate करना है, so then the reagent that you will use is toluene and hexane, which is option C. So saving and moving on to the next, we have state which of the following statement is true or false. P, if temperature increases, UV radiation absorption increases. Q statement states that if temperature increases, better is the UV. So which of the following is your answer? Option A states P and Q are true. Option B states P and Q both statements are false. Option C states that P statement is true and Q is false. And option D states that P statement is false and Q statement is true. Now, let us evaluate these two statements carefully. What does statement P states? If temperature increases, UV radiation absorption increases. Yes, why? Because when the temperature is increased, the viscosity of your sample solution also decreases owing to the temperature. Possibly because of that, a bathochromic shift happens. Why? Because temperature has a very important factor in shifting your wavelength to the higher wavelength. So bathochromic shift will occur if the temperature of your solution is slightly increased. So that is the reason why you have to maintain optimum operating conditions when you are using the UV spectrophotometer. Because both the bathochromic shift and hypsochromic shift will not help you evaluate the exact accurate lambda max of your compound. And option Q statement said that if temperature increases, better is the UV. Better is the UV means what? Better is your UV analysis. So basically temperature अगर increase हो रहा है, bathochromic shift हो रहा है, तो obviously you are not going to get the exact lambda max of the value. Why? Because the compound has interacted with the temperature, and because of that it has shifted its wavelength to a higher wavelength. So any sample which is getting affected owing to the temperature or because of the solvent effects or any of the conditions, or because of maybe oxochromes or chromophores present in your compound, and because of that, if there is any resulting bathochromic shift or hypsochromic shift or any shift occurring, then your UV analysis will never be better, because it will never help in exact prediction of the exact lambda max. So suppose मेरा exact lambda max is 250 nanometer, बट अगर मैंने टेम्परेचर बढ़ाया या मेरा रूम टेम्परेचर ज्यादा है, तो यूवी एनालिसिस के टाइम पे क्या हो सकता है कि 250 अगर मेरा wavelength है, so instead of 250 nanometer, because of bathochromic shift, I might get 260 nanometer or 270 nanometer as my answer, which will again lead to the incorrect or inaccurate analysis. So your answer is P is true. That means if temperature increases, UV radiation absorption increases. मतलब क्या, temperature बढ़ेगा तो bathochromic shift होगा, लेकिन temperature अगर बढ़ेगा तो UV analysis better नहीं होगा. So your answer is option C, which is P statement is true and Q is false, because an increase in temperature, and if it is leading to an increase in absorption, then it will never lead to a better UV analysis. Moving on to the next, which sentence is false about inorganic compounds? Ag has more absorption of UV radiation. AU has more absorption of UV radiation. Inorganic compound has less absorption of UV radiation. And option D is the inorganic compound has a high absorption of UV radiation. Now, if you look at the options carefully, Ag has more absorption of UV radiation. That is, what is Ag? If you know, so because it is an element, and also your UV radiation is not specific to elemental analysis. So Ag is nothing but your silver. So silver is inert and it is not going to be highly affected and will not have more absorption in the UV radiation. And it is not specific. Why? Because silver is something which is a solid, and in UV analysis basically it is used for solids and your liquid sample. So even if you're having a solid sample, you have to prepare a solid solution mixture. That is, you have to dissolve the solid in a particular solvent and prepare a mixture of it. So it is never possible to prepare silver in a solution form and analyze it by UV. Second option is gold, which is AU, has more absorption of UV radiation. Again, you cannot prepare a gold solution for analysis by the UV, because again, you cannot suspend your gold element and you cannot solubilize it in a suitable solvent and analyze it. So option A and B is not your answer. So and it is also UV spectroscopy analysis is never element specific. So option A and option B is eliminated. We have option C, inorganic compound has less absorption of UV radiation. And option D, inorganic compound has high absorption of UV radiation. So which of the sentence is false? So among the following is that, again, as I said, option A is not applicable. Option B is also not applicable. So we have eliminated that. Now the question says that which sentence is false about inorganic compounds. So option C and D, since we have eliminated A and B, let us estimate option C and D. C option क्या बोलता है? Inorganic compound has less absorption of UV radiation. Option D says inorganic compound has high absorption of UV radiation. Now you know that most of the solvents which you are using in your UV analysis, it is all basically you're going to use methanol, or you're going to use solutions which are non-polar. So the option which is incorrect or false among all of these four options is option C. Inorganic compound has less absorption of UV radiation. It is not true. Why? Because inorganic compound have high absorption of UV radiation. So option A and B is not applicable. Option C or D may say the incorrect solution, the incorrect option is option C, that is inorganic compound has less absorption, which is not true. Why? Because inorganic compound always have higher absorption in your UV. So simple hai, my answer is going to be C. So you have seen that in almost like I can say 45 minutes, we have solved 18 questions. So we have only 2 more questions to go. So moving on to the next. Which of the following detector has a fast response time? Option A, photomultiplier tube. Option B, phototube. Option C is a photodiode array. And option D is a barrier layer cell. So the option for the solution to this is it cannot be photomultiplier tube. Why? Photomultiplier tube does not give quick results. Also, phototube will also give you delayed results because it takes more time for analysis if you're using phototube as a detector. Rahi baat photodiode array. So as you know, photodiode array is an array of multiple photodiodes. So basically multiple intensities can be detected at the same time. So because of this very reason, because multiple detections can take place, the photodiode array is supposed to have the fastest response time compared to all of these detectors here. So barrier layer cell is also not your answer. So your answer is the detector which has a very fast response time is your photodiode array. I hope it is all clear how we are approaching all these. Moving on to the next. Which radiation source has electrodes in its construction? We have the tungsten lamp, we have the hydrogen discharge lamp, we have the xenon discharge lamp, and option D is your mercury lamp. Now, which of the following will have electrode in its construction? As we all know, what is a tungsten lamp? It is nothing but a lamp with a filament of tungsten. So option A is not your answer. Option B is hydrogen discharge lamp. Now, hydrogen discharge lamp has electrodes, and option C, xenon discharge lamp, it does not have electrodes, and mercury lamp also does not have electrodes. So, because mercury lamp is just a lamp which has mercury in it, and xenon discharge lamp also does not have electrodes. So, the only possible electrode which has hydrogen in it, the only possible electrode containing radiation source is nothing but your hydrogen discharge lamp. Why? Because it has your electrodes in it. So that is all. So this is how we will approach the MCQs, and the option I will select the correct option first, hydrogen discharge lamp. So you can see that in 45 minutes I have solved all of these MCQs. So this is how we are going to solve the question. So in UV visible spectrophotometer, you have to be very careful to solve all these MCQs in this order, such that you have to remember the calibration parameters, the substances used for calibration. Then you have to know the basics, that is the basic range of UV, which is a UV range, which is the visible range, which is the vacuum range. Then you have to study about the various solvents which are used in UV, like which of them are not UV transparent, or which are not applicable to UV spectroscopy and which can be used for UV spectroscopy. Those list of solvents also you need to know. You need to memorize the alkyl substitution values based on the Woodward-Fisher rule. So which functional group is having the basic wavelength value or the lambda max value, that you have to know and memorize when you are solving the chapter of this equation. When you're solving the MCQs of this chapter. And also you have to study about the various applications, the material of construction of your UV spectrophotometer, also the various detectors which are used, the function of the detectors, and also the phenomena, that is how the shift or change in absorbance might occur, and what compounds or which materials or which solvent or whether temperature factors can affect your absorption. So that is all you have to know about UV. So if you read all these, I think it would be sufficient enough to solve the MCQs of this chapter. So I think I will conclude with this. So that is all for today. So we will submit our test and we will conclude with our lecture. I hope this session was interactive and you have learned something out of it. So let's submit the test. See, I have saved 15 minutes of my time. Thank you, everyone. So we'll end our session here.